Everyone to exclusive tutorial again. This is our second video on simple harmonic motion. I would advise that if you've not watched the first video, please do wait to look for it in the playlist. Watch the first video before coming to this one because it's actually make things very easy for you. Okay? In our previous video, we talked about the basics of simple harmonic motion and some useful equations, and I explained how the body undergoing simple harmonic motion looks like. In practice, I made use of a simple pendulum. Now, next thing we're going to be talking about is the energy involved in simple harmonic motion. Okay? The energy involved in simple harmonic motion. Now, one important thing is that when we define some useful terms in simple harmonic motion or in circular motion in general, we don't define them like we are defining some linear quantities. Okay, there are several things that vary. Now, we only talked about the displacement, the velocity, and the acceleration of a body undergoing simple harmonic motion, especially a simple pendulum. So, since we are talking about the energy, we might want to also talk about the energy in this simple harmonic motion. Now, basically, there are two types of mechanical energy because the system I'm going to be considering is only the mechanical system of this simple pendulum. Basically, we have two energy: the mechanical energy, which is divided into two. We have the kinetic and the potential energy. Okay. Now, the kinetic energy is the energy possessed by a body due to its velocity that it is possessing, and the potential energy is the energy formed in the body by virtue of its height or position. Now, looking at this diagram, you might want to know where the kinetic energy is highest, where it is minimum, as well as the potential energy, where it is highest and where it is minimum. Now, for this midpoint or for the mean position, the kinetic energy at this point is maximum. Why is the kinetic energy at this point maximum? We know that kinetic energy mathematically is 1 over 2 mv squared, and 1 over 2m is a constant. So kinetic energy varies directly as the velocity of the body, telling us that as velocity increases, kinetic energy tends to increase. Coming to this diagram, velocity is maximum at this point. So if velocity is maximum, kinetic energy obviously will be maximum too. So at this point, kinetic energy is minimum. That should tell us that kinetic energy at this point is minimum, and at this point it is maximum. Okay? And for potential energy, we know that potential energy is given mathematically as mass times gravity times height. Mass times gravity is a constant. The mass of the body does not change during its course of motion. And g is acceleration due to gravity, 10 meters per second or 9.8 meters per second squared. Okay? Potential energy is equal to mgh. So if these are constant, potential energy tends to vary with the height of the body. So increase the height causes an increase in potential energy correspondingly. Okay. Now, initially in our previous video, I told you that the height of the body increases from this point to this point, because if we should trace it, we notice that there is a change in the height above the ground. So height has increased at this point, and it is maximum at this point. Okay. So it means potential energy has to be maximum at that extreme. Potential energy is maximum at this point, telling us that potential energy is minimum at this point. So basically, these are the parameters you have to know before we come back to the energy of a simple harmonic motion. Now, for a simple harmonic motion, the mechanical energy is divided into two parts. The mechanical energy is divided into two parts: the kinetic and the potential energy. Okay? And since we say the body is having kinetic and potential energy, it cannot have the two at the same point, maximum, or both of them minimum. One has to be maximum and the other point, the other one has to be minimum. So at this point, we are having kinetic energy, full kinetic energy, okay, at first items in motion. And for the potential energy, it is equal to 0, there is no height, okay. And at this point, potential energy is maximum, kinetic energy is minimum. So the energy is conservative, except for the fact that frictional forces are dissipating it in the air as it moves through it. So what if at the point here we want to know the kinetic or the potential energy or the mechanical energy? To get the mechanical energy, we simply take the sum of the kinetic energy at that point and the potential energy at that point. So we can say mathematically that mechanical energy is equal to potential energy plus kinetic energy of the body. Okay, or kinetic energy plus potential energy of the body. Now we already know that kinetic energy is 1 over 2 mv squared. How about potential energy? Potential energy, of course, is mgh, we know. But in this case, we're not going to be making use of mgh. Looking at the string that is holding this ball to a fixed position, the string must not be inelastic. Must be inelastic rather, that is, it must not expand or extend. Okay? Now, this string, we are going to assume that it does not extend or compress. For that reason, we are going to make use of the inelastic or elastic potential energy from Hooke's law of elasticity. Mechanical energy is equal to elastic potential energy, and elastic potential energy is given as 1 over 2 kx squared, where k is the constant, force constant, or Hooke's law constant, and kinetic energy is 1 over 2 mv squared. Now, looking at these two expressions on the board for potential and for kinetic energy, what we want to do is simplify these guys down and see what we obtain at the end. Okay? There are some several quantities you can factor out. 1 over 2 is common, so we are going to have 1 over 2 in brackets kx squared plus mv squared. Okay? Now we talked about the displacement, which is in our previous video. I'm going to write it up here again. The displacement for a body in simple harmonic motion is given as x is equal to a sin wt plus phi. You already know the useful meanings. And then velocity, you can get the velocity by differentiating this guy, which is the derivative of displacement. And that gives us aw cosine of omega t plus phi. Okay, that is the derivative of the velocity. So what we want to do is substitute those two equations into this formula you are seeing here. And we'll substitute, we are going to have 1 over 2 in brackets. K is a constant, okay, first constant k, and the displacement is a squared sine squared omega t plus phi. Okay, I just expanded x, which is a sine wt plus phi, when it is having squared directly instead of writing it again, plus m, velocity, is aw cosine wt plus phi. So expanding directly, we are going to obtain a squared w squared cosine of squared omega t plus phi. Okay, this is the formula we're going to obtain. We can't just count this formula as this is kind of unclear to most people. Okay, so what we are going to do, we are going to break down this formula and we'll be seeing the results or the resultant mechanical energy of the system. Now, also we can see that some quantities might be common. Example, a squared. So our factoring out a squared will give us a squared over 2. Of course, we have 1 over 2 outside. And then we're going to be left with k sine squared omega t plus phi plus, making out a squared, you're left with mw squared cosine squared omega t plus phi. Now, also there is a relationship between force constant and angular velocity. It is quite a very useful and good relationship that we have to take note of. And that relationship is omega equals square root of force constant over mass. Okay? Omega equals the square root of force constant of mass. That formula can be derived in circular motion. And I advise you guys to also watch the videos on circular motion to ease you with that aspect. Okay? Omega is equal to square root of k over m. I can choose to substitute it in this point, or I can choose to substitute it at this point. Okay? Now, let's choose to get omega squared m. Omega squared m. To get it, we are going to first of all square both sides and then multiply both sides by m. When I do that, I'm going to obtain omega squared m is equal to k. Now, I want to substitute for omega squared m into this equation right here, giving us a squared over 2 in brackets k sine squared omega t plus phi plus, now m omega squared is k, so I'm going to get k cosine squared omega t plus phi. Okay, now this is the resulting formula. K is also a common quantity between these two guys, so we can factor it as giving us a squared k over 2 into brackets sine squared omega t plus phi plus cosine squared omega t plus phi. Okay, this will be the resultant equation. Now we call from trigonometry that sine squared of a function plus cosine squared of a function is always equal to 1. So everything in this bracket gives us our answer as 1. Okay, we're going to get a 1 in this equation. So 1 times everything here, we're going to be left with, of course, the quantity involved there is mechanical energy. Mechanical energy is equal to 1 over 2 Ka squared. Now this one is the formula for calculating mechanical energy. You can see that the mechanical energy depends on the amplitude. That is, the farther we displace it at first instance, the more energy the system is going to have. Okay, of course, we know it causes a corresponding increase in height, which should tell us that potential energy has increased. Since we displace it at a farther distance, we're going to get more velocity, which increases the kinetic energy, and so therefore it means mechanical energy is also going to increase. Now, what if we're having a question that does not contain the amplitude or the k constant for that equation? We can also substitute in for k at this point. We know that k is w squared m. So when we substitute, we are going to get mechanical energy equals 1 over 2 omega squared m. Okay, this is another formula for calculating the mechanical energy of a body in this system. I hope you guys understood this part very well. The energy, you can choose to go over the video over and over again for you to get it perfectly. Now the next part we're talking about is the maximum velocity and the velocity of a body in simple harmonic motion. We've already talked about where acceleration is maximum and where it is minimum, and also the normal equation for acceleration and also displacement in our previous video. So in this one, we're going to be talking about that of velocity. Where do we get the maximum velocity and what is the equation? And also the velocity at any point in time or space of a body in simple harmonic motion. Okay, that's the next thing we're going to talk about. Now, for a body in simple harmonic motion, how do we know the velocity? We just proved that mechanical energy is equal to kinetic energy plus potential energy. Okay, and mechanical energy's formula was proven as 1 over 2 k. Okay, let's make this of the other one. 1 over 2 mw squared a. Okay, this was one of the formula that we made use of, or 1 over 2 k a squared, if I'm not mistaken. Okay, 1 over 2 k a squared, and kinetic energy, this k squared, please. And kinetic energy is 1 over 2 mv squared, while potential energy is 1 over 2 kx squared. Okay, now still looking at this formula, some quantities can cancel out. 1 over 2 is a constant, can cancel out in the 3 parts, and then we are going to be left with mw squared a squared equals mv squared plus kx squared. Okay, this is what we are going to be left with, mw squared kx squared. Now from here, I want to make velocity subject formula because this is what we are looking for. So we can say that mv squared is equal to mw squared a squared minus kx squared. Okay, and then looking at this formula again, dividing through by mass, we're going to obtain v squared equals w squared a squared, because we've divided through by the mass, minus k over mx squared. Okay, minus k over mx squared. Now k over m should look familiar because I've shown the formula on the board before. Remember I said that omega is equal to square root of k over m. So omega squared will be equal to the k divided by m. We can just substitute directly for omega squared, giving us velocity squared to equal omega squared a squared minus k over m is omega squared, to get omega squared x squared. Now we cannot factor out omega squared because it is common. Therefore, velocity squared will equal omega squared in brackets a squared minus x squared. Okay, Now take square root of both sides because we want to make v the dependent variable and not v squared. Therefore, velocity will equal square root of omega squared is omega, so we get omega square root of a squared minus x squared. Now, we should take note that this is the formula for calculating velocity. As a point in time when we have displacement value and other quantities in space for a body undergoing simple harmonic motion. Okay, x is displacement, a is amplitude, omega is angular velocity or frequency, and v is the velocity. Now, when we get the maximum velocity, we'll come back to our diagram again. We know that acceleration is maximum at the ending and minimum here, but for velocity is maximum here and minimum at that extreme. Okay, now at the point where velocity is maximum, since it is quantity we want to obtain, velocity which is maximum at this point, where displacement is equal to 0 or displacement does not exist, okay, the displacement is equal to 0. So to get the maximum velocity, we are going to plug in the value for displacement as 0. Okay, to plug in for the maximum displacement, you can say velocity is maximum when displacement, which is x, equals 0. So plugging it into this formula, we are going to get v equals omega square root of a squared minus 0 squared. Then v will be equal to, when we simplify this, we should get omega a. Okay, this is what we are going to get. So v is equal to omega a gives the maximum velocity for a body undergoing simple harmonic motion. Now, there are other parts of simple harmonic motion we are going to talk about. Because there are various examples of bodies undergoing simple harmonic motion, example is a simple pendulum. I made use of a simple pendulum formula to derive, a simple pendulum diagram to derive the equations, as you can see in the video. Now, the other ones we're going to be dealing with are the one involved in a helical spring, that is a loaded spring, okay? That is spring containing a mass or an object. And then we also have for a loaded test tube immersed in a liquid. Those other two videos will be dropped, but not with this one, okay? So I would advise you guys to go through these examples and the videos I've given on the illustrations on the board. Do wait to like, share, and if you have a question, also do it in the comment section. We are going to respond, or if you want a video for us to create, we are going to answer it immediately and do that for you. Okay, provided it is within the scheme or the courses that is outlined in the section.